A cart with mass m is pulled along a level dynamics track as shown above. A force sensor is attached to the cart with a string and used to measure the horizontal force exerted on the cart to the right. A motion sensor is used to measure the acceleration of the cart with the positive direction toward the right. Friction is not negligible. On the dot below, which represents the cart, draw and label the forces, not components, that act on the cart. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So the first thing we can write down is friction, because it says friction is not negligible. So usually friction is a fairly small force, so we can label it as pretty small. So the positive direction is towards the right, and friction is pushing against the cart in the negative direction, so we draw it to the left, very small, and label it force of friction with a little f. Then we can do force of tension for the string, that pulls the cart to the right. That's a much larger force, so that would be force of tension, T for tension. And then we have the force of gravity pulling down, Fg, that equals mass times g, the gravitational constant, and then the normal force points up. And since the cart is not moving up or down, the force of gravity and the normal force must be equal. They must cancel out, so we can do a little dash mark to show that they're equal. A student pulls the force sensor with a constant force and the cart accelerates. This is repeated for several trials with a different constant force used for each trial. The data are recorded in the table below. Now, on the grid below, plot the data points for the acceleration of the cart as a function of the force sensor reading. Clearly scale all axes. Draw a straight line that best represents the data. The first thing we need to do is pick an accurate scale. So we can notice that the force sensor reading doesn't go below 0.3 and it maxes out at 0.6. So if we should start the x-axis at 0.3, not 0, otherwise we'll end up with a bunch of redundant space kind of in this area. So let's do 0.3 to start, and then we notice we have 1, 2, 3, 4, 5, 6, 7 major ticks, and it changes by around 0.3 for the whole time. So 0.6 minus 0.3 is about 0.3. So if we do 0.05 per tick, that would get us to right here for our final reading on the x-axis. So we can do 0.05. So doing that. Perfect. For the y-axis, we could just start at 0 since 0.12 is much closer to 0 than 0.32. So we start at 0. It goes up to 0.7. So there's 5 ticks, goes up to 0.7. If we do 0.2 per tick, that would put 0.7 around here. So that's more than half the graph. And so let's do that. Now all we need to do is label our points. So I'll do that right now. And done. Now we need to draw a straight line that best represents the data. So doing that, we get something like this. Now I have gone ahead and done some of the calculations for this next part since they get a little bit numerical and they wouldn't be interesting to see done out by hand. So our next part is using the straight line from the graph, calculate the mass of the cart. So one thing we can notice is newtons is actually kilograms meter per second squared, and acceleration is meters per second squared. So if we divide newtons over acceleration, meters per second squared cancel out, and we're left with just kilograms, which gives us the mass of the cart. So the newtons are on the x-axis and acceleration is on the y-axis. So we can use, instead of rise over run for slope, we'll do run over rise, which is the reciprocal of the slope. So on the numerator, I have 0.56 is the x-coordinate of this point, and then 0.4 divided by 0.64 is the y-coordinate minus 0.28, and that gives 0.16 over 0.36, and that's 0.444 kilograms. That goes on forever, so we can just round it about there. So now we can use a straight line from the graph to determine the magnitude of the force of friction. So one thing we can notice is the force of friction cancels out the force sensor reading, which eventually results in an acceleration that's 0. So when that happens, when the force of friction exactly equals the force sensor reading, that happens at the x-intercept, the horizontal intercept on the graph. So we can use a straight line, extrapolate this out a little bit past our 0.3 edge, and kind of draw the ticks in ourselves, and that gives 0.27 on the graph for our horizontal intercept. So that's our force of friction. And since the units are newtons, the units of the force of friction is also newtons, so 0.27 newtons is our final answer. Part C. The above experiment is repeated by using a constant force sensor reading of 0.45 newtons. The cart starts from rest at time t equals 0 seconds and is pulled for a time of 2.0 seconds along the dynamics track. So part I, determine the acceleration of the cart. So we could look at our line of best fit around 0.45 newtons and guess that the acceleration, sorry you can't see that, the acceleration should be around 0.38, about there, that's about 0.38. But the AP graders might be looking for a more in-depth solution than that. So we can remember that acceleration equals net force divided by mass. And in this case, the net force is the force sensor reading force minus the force of friction. So that would be the force of tension, going back to our free body diagram from before, and that's minus the force of friction. So minus force of friction over m. Plugging our values in, we get our force sensor reading force is 0.45 minus the force of friction we just found to be 0.27, and our mass was 0.444. From there and there I'm getting those numbers, and that equals about let's see, 0.405 meters per second squared. That's close enough to 0.38, so I think that's a fair answer. As 0.05, 0.38. You're very close, so that's a good answer. Part 2. The string breaks at time t equals 2 seconds. Calculate the time it takes for the cart to stop after the string breaks. So first, let's figure out how fast it's going after right when the string breaks. So we can use v equals v0 plus at, and v0 is 0 since the cart starts at rest, and acceleration is 0.405 meters per second squared from before, and time is 2 seconds. So v equals 0 plus 0.405 times 2, which equals 0.810 meters per second. So we want, now we can use the same equation, but the final velocity is going to be 0, and the initial velocity is going to be 0.810, and then the acceleration is going to be caused by the friction force. So now we can use, again, over here, acceleration equals F net, not met, over m, which equals the friction force is 0.27 newtons, and it's negative, so it's negative 0.27 The mass is 0.444 kilograms again. So acceleration negative 0.27 over 0.444, which equals 0.608. So we plug this in, minus 0.608 t, and t is the time it's going to take for the cart to stop. So rearranging 0.608 t equals 0.810. So t equals 0.810 over 0.608, which equals 1.333 seconds. The experiment and analysis in parts A and B are repeated with a cart that has the same mass but a greater force of friction. Part D. Will the slope of your new line be greater than, less than, or equal to the slope of your line in part B? On first glance, you might be tempted to say that the slope is less than in part B because a greater friction would result in smaller accelerations, right? That's true, but the ratio of the force of friction to the force sensor reading stays the same, and so it doesn't change the acceleration at a different rate. The force of friction is still constant, so a greater force of friction would move every point on this graph down by the same amount, because it would cancel out the force sensor reading by the same extra little amount. So it would shift the whole line down. So that doesn't change the slope. It makes every point on the line lower, but it does not change the slope. So our answer is equal to. You can check that there. Will the horizontal intercept of your new line be greater than, less than, or equal to the horizontal intercept of your line in part B? Same idea as before. A greater friction force will lower the entire line by the same amount. So if you lower this whole line, you can imagine that if you kind of shift this whole thing this way, that the horizontal intercept is going to move to the right, so it's going to be greater. So our answer is greater than. And we're done. Problem 1 complete. Problem 2. A block of mass 2m rests on a horizontal frictionless table and is attached to a relaxed spring, as shown in the figure above. The spring is non-linear and exerts a force f of x equals negative bx to the third power, where b is a positive constant and x is the displacement from equilibrium for the spring. A block of mass 3m and initial speed v0 is moving to the left as shown. Part A. On the dots below, which represent the blocks of mass 2m and 3m, draw and label the forces, not components, that act on each block before they collide. Each force must be represented by a distinct arrow starting on and pointing away from the appropriate dot. So let's start with block 2m. The spring, as the problem says, is relaxed, so it's not exerting any force on the block. So the only forces left, since it's not in motion either, are force of gravity, so F of g, and that equals mass times g, so that's 2mg, and then normal force, so we can call that Fn2, and the little 2 denotes that it's block of mass 2m. Now for the block of mass 3m, same idea. It's moving to the left, but there's no force on it, there's no acceleration, so the force of gravity equals 3mg instead of 2mg, and the normal force, we'll call that Fn3. And these two forces are the same, and these two forces are the same, since neither block is moving up or down. The two blocks collide and stick to each other. The two-block system then compresses the spring a maximum distance d, as shown above. Express your answers to parts B, C, and D in terms of m, b, v0, and physical constants as appropriate. Part B. Derive an expression for the speed of the blocks immediately after the collision. So, from conservation of momentum, we know momentum is conserved in every collision when there's no external forces. So, we have the initial momentum can be given by mv for block 1 and mv for block 2, and we can add those up. So, the block with mass 3m had its mass 3m. So we write 3m, and then it had velocity v0 to the left. So if we let v0 to the left, that can be our positive direction. So we'll denote that as positive. So 3m times v0 plus 2m for the mass, the 2m block right here, times the velocity is 0, and this all equals, at the end, the mass of this whole two-block system is 3m plus 2m is 5m, and we'll let the final velocity be vf. So rearranging this, we get 5m vf equals, which is 3m v0, equals 3m v0, and then dividing both sides by m cancels. Dividing both sides by 5, we get vf equals 3/5 v0. Part C. Determine an expression for the kinetic energy of the two-block system immediately after the collision. So we can use the equation kinetic energy equals 1/2 mv squared. We have the mass of the total system is 5m. 2m plus 3m is 5m. So 1/2 5 times 5m times 3/5 v0 squared, because that's our velocity. And this evaluates to, if we put all the constants out front, 1/2 times 5 times 3/5 squared is 9/25 times m v0 squared, and this comes out to 9/10 m v0 squared, like that. Part D. Derive an expression for the maximum distance d that the spring is compressed. So this equation isn't on our green sheet, but it's an important one to know. We have the force given by the force associated with a potential energy function u is given by the negative derivative of that potential energy function with respect to displacement. So we can integrate this to get from 0 to f, or to d, from 0 to d. That's the maximum displacement of the spring d. That integral 0 to d for the total potential energy of the spring, f dx, equals negative u. So that's the negative of the total potential energy stored in the spring. So before the spring compresses, it has total mechanical energy 9/10 mv0 squared. We just found that. And it has no potential energy stored in the spring, since the spring is completely relaxed when the blocks collide initially. So we have negative u is equal to negative 9/10 mv0 squared. So we can write this over here. So negative 9/10 mv0 squared equals negative u. And then the force is given by this function, negative bx cubed. So then this integral becomes 0 to d, negative bx cubed dx. So we cancel the negatives to make things look nicer for us. And then this becomes 9/10 mv naught squared, doesn't change. This evaluates to this negatives cancel, that's not a variable or anything. So this, the antiderivative of bx cubed is bx to the fourth divided by 4. So that's just bx to the fourth divided by 4. Write that down. And then using the fundamental theorem of calculus, we plug in d to get the first value. So that's b d to the fourth divided by 4 minus, and then we just plug in 0 to get the second value. So b times 0 to the fourth over 4. That becomes nothing because 0 to the fourth is 0. So we can bring this whole thing up here. bd to the fourth over 4 equals 9/10 mv naught squared. Multiplying both sides by 4, we get 36 over 10, which becomes 18 over 5. Dividing both sides by b, we get d to the fourth equals 18 mv naught squared over 5b. And all we have to do to finish is take the fourth root. So we get d equals the fourth root of 18 mv naught squared over 5b. There's our answer. My notes over here. Part E. In which direction is the net force, if any, on the block of mass 2m when the spring is at maximum compression? Left, right, or the net force on the block of mass 2m is 0? Well, we can look at the potential energy function. Again, that's the wrong problem. Let's see here. You can look at the potential energy function again. Here's a blank sheet for this problem. And it's given by f of x is negative bx cubed. So when the displacement is positive, the force is negative. So in this case, the displacement is positive in the left direction, so the force is negative in the right direction, because remember, we said that the left direction is positive and the negative direction is right. Or yeah. So if we have a positive displacement d to the left, then we must have a negative force from the spring right. That's the only force applied to the block of mass 2m, so our answer must be right. Part 2. Which of the following correctly describes the magnitude of the net force on each of the two blocks when the spring is at maximum compression? The magnitude of the net force is greater on the block of mass 2m, same thing, but on the block of mass 3m. On each block has the same non-zero value, or the net force on each block is 0. So that both blocks, since they're stuck together, again, they're stuck together, both blocks had the same acceleration. However, F equals ma still applies, so since the block of mass 3m has a greater mass, it must also have a greater force in order for it to have the same acceleration as the block of mass 2m. So the magnitude of the net force must be greater on the block of mass 3m for it to have the same acceleration. Part F. Do the two blocks which remain stuck together and attached to the spring exhibit simple harmonic motion after the collision? Couldn't tell you because we haven't learned this yet. A uniform rod of length d has one end fixed to the central axis of a horizontal frictionless circular platform of radius r equals 2d. Fixed at the other end of the rod is an ideal spring of negligible mass to which a block is attached. The block is set in frictionless grooves so that it can only move along a radius of the platform, as shown in figure 1 above. The equilibrium length of the spring is d over 2. Below is a table showing the mass of the block in the masses and rotational inertias of the rod and platform. A motor begins to slowly rotate the platform counterclockwise as viewed from above until the platform reaches a constant angular speed omega. Under these conditions, the spring has stretched by an additional length d over 2, as shown in Figure 2. Answer the following questions for the platform rotating at constant angular speed omega. Express all algebraic answers in terms of m, d, omega, and physical constants as appropriate. Part A. Derive an expression for the spring constant of the spring. We can use two equations here. The first is the one for centripetal acceleration. AC equals v squared over r. The first manipulation we can make is based on the fact that v equals omega r. We can plug that in, and this becomes omega squared times r. We also have that r in this case equals 2d, since the block is all the way to the edge of the platform, and the platform has radius 2d. So we can plug in 2d, this becomes 2d omega squared. Then we can use Newton's second law, F equals ma. Plug in, we have just m equals m, and a equals 2d omega squared to get F of the force on the block is equal to 2md omega squared. The force of the block can also be given by the equation F equals negative kx, where k is a spring constant and x is displacement. We can ignore the sign since that's directional and we only care about the magnitude of the force. And we have that the displacement is equal to d over 2. So this equals, so the magnitude is equal to kd over 2. So these must be equal. So we can equate them over here. 2md omega squared equals kd over 2. Multiply both sides by 2, and we can flip the equation around, so we get kd equals 4md omega squared. Cancel d from both sides, and we get k equals 4m omega squared. Part B. Determine an expression for the rotational inertia of the block around the axis of the platform. So for this, we can remember the equation I equals mr squared. The block has mass m, and it has its radius 2d from the axis of the platform, 2d. So this just becomes plugging in m is m, and 2d is r. 2d squared is 4d squared, so we get 4md squared. Continuing part B, derive an expression for the rotational inertia of the entire system about the axis of the platform. The inertia of the platform about its axis is given by this equation, mpr squared over 2. So remember, we can only have our answer in terms of m, d, and omega, so we need to use either m, d, or omega in these variables instead of mp and r squared. So we have mp is equal to 5m, so we can substitute in 5m. And then for r squared, we are given r equals 2d. 2d squared is 4d squared, so we plug that in. 5m times 4d squared over, then it says, what does it say, 2. So this is I platform equals, and this all equals 10 md squared. The inertia of the rod about an end of the rod is given by this equation. One end of the rod is at the central axis, so we can still use this formula. So we plug in 3m for mr, d squared is fine. So 3md squared divided by 3, we cancel the 3, and this just becomes md squared. So we have IR just equals md squared, and then I block we just found to be 4md squared. 4md squared. We simply add all these up to get I total equals 10md squared plus md squared plus 4md squared. This all just equals 15md squared. Part C. Determine an expression for the angular momentum of the entire system about the axis of the platform. For this, we can recall the equation L for angular momentum equals inertia times omega. We just found inertia for the entire system is 15md squared. And we can use omega just as omega, so we're done. Easy. While the system continues to rotate, a small mechanism in the pivot moves the rod slowly until the center of the rod is positioned on the axis, as shown in figure 3 above. The same constant angular speed omega is maintained by the motor during driving the platform. Part D. Derive an expression for the distance x that the spring is stretched when the rod reaches the position shown in figure 3 above. For this, we can use the same method we did before. So first, we have F equals ma, and a is centripetal acceleration again. So AC equals v squared over r, which is equal to omega squared r. And in this case, r is going to be, this length is d over 2 here, since it's half the rod and the rod is length d. This is also d over 2. That's a 2, not an r. So this whole length here, r, for the rod, is d plus x. So r is w squared d plus x. Excuse me, centripetal acceleration is omega squared times d plus x. If I was saying w, I meant omega. So plugging this back in, F equals m omega squared times d plus x. And in this case, we have for F, magnitude of F equals kx. In this case, again, the displacement for the spring is just x in this case. It's just x. So we can leave this as it is. And k, as we found before, is 4m omega squared. So this equals 4m omega squared x. Now equating these two, we get 4m omega squared x equals m omega squared times d plus x. Cancel this, we get 4x equals d plus x. And then 3x equals d, and dividing both sides by 3, x equals d over 3. For parts E, F, and G, assume the center of the rod is still moving towards the axis of the platform. Part E. Is the angular momentum of the entire system increasing, decreasing, or staying the same? For this, we can go back to the equation L for angular momentum is inertia times omega. Omega stays constant, which is given for this problem, but since everything is shifting towards the center, and inertia is smallest when everything's at the center, inertia must be decreasing. So since this is constant and this is decreasing, the other side of the equation must also be decreasing. And this is angular momentum, so our answer is decreasing. Part F. In order to keep the system rotating with constant angular speed omega, is the motor doing positive work, negative work, or no work on the rotating system? For this, we can consider all of the sources of mechanical energy. So one source is kinetic energy, linear translational kinetic energy, and that's given by the formula, not translational kinetic energy. We want rotational kinetic energy. That's given by the formula K E equals 1/2 I omega squared. So this is for the same reasons as on this problem. Omega is constant, so this stays the same. I is decreasing, so this decreases, meaning rotational kinetic energy must decrease. So this decreases. And then we have potential energy is stored in the spring. But in this case, the spring had more displacement when the block was farther from the center. So d over 2 is greater than d over 3 when this is closer to the center. And the more displacement in the spring, the more potential energy. So reversing that, the closer the spring gets to the center, the closer the block gets to the center, the smaller displacement becomes and the smaller potential energy becomes. So potential energy of the spring also goes down. There are no other sources of energy in the diagram. So because of that, total energy decreases, and in order for that to happen, there must have been negative work done on the system. Part G. On the block in figure 4 below, draw a single vector representing the direction of the acceleration of the block. Draw the vector so that it is starting on and pointing away from the block. So the law of inertia says that this block in this position wants to go directly in this direction. However, we need it to stay going in a circle, so it needs to travel in this path instead. So something needs to pull it back in this direction by some amount to cancel out the leftward motion, and something must pull it down in the y direction to keep it going downwards. So our arrow must be in this quadrant somewhere, so we could draw an arrow like this, and this should be good. We're done.